I have shown you how the Laplace transformation can be used to solve a linear ordinary differential equation with constant coefficient. Of course, I only took a simple example of a first order differential equation. We are not going to solve differential equations using the Laplace transformation, so I will not take more examples or higher order examples, but I hope the idea is clear. To go over it once again, suppose we have a differential equation of first order dx plus a0x equal to u is the input, x is the response, u will be specified as a function of time, the initial value x0 or x0 plus will also be specified, and the problem is to find out x as a function of time, x of t. So as we saw, if you apply the Laplace transformation to this equation, then from that we got an expression for capital X of s, the Laplace transform of the desired response function x of t. Just going through it very quickly, dx on transformation gives you s x of s minus x0 plus a0 x of s equal to u of s, and therefore x of s, if you remember, was the sum of two terms. One of them involved the initial condition x0 plus divided by s plus a0, and the other term was 1 over s plus a0 multiplying u of s. Now if you wanted the solution of the differential equation, then of course it is necessary to know what u as a function of time is, to know what its Laplace transform us is, to be known, to be given also the initial value x0, and then do the Laplace inversion of the right hand side here. And we saw that this part or this term corresponds to the 0 input response, and the second term corresponds to the 0 state response. So if you want to find out the solution x explicitly as a function of time, one will have to do all this: know what ut is, calculate u of s, and then work out the Laplace inverses of these two parts. That will give you the expression for xt. Now as I said, we are not basically interested in solving differential equations, but in trying to find out something about their behavior, that is, how does the response vary for a given input, or if I change the input, in what way will the response change, and things like that. Now as we see here, the response is already in two parts, or rather the response is a sum of two parts. Physically, of course, these two parts are not separate. You start the system in some non-zero initial condition and thereafter apply an input and you get the total response. It does not come into two parts separately. So what you can observe is only x of t, but in theory, or when we do the analysis of it, x of t consists of two parts. One is the 0 input response and the other is the 0 state response. Now therefore, in what we are going to do very soon, we will keep these two terms separate. In fact, for some time we will keep aside the 0 input response part of it. In other words, alternately we can say that we are assuming that the initial condition is 0. Now in fact that is not a good way of looking at it, because the initial condition may not be 0. For example, suppose the motor has been running for some time, and when I start looking at it, that is my t equal to 0, I suddenly change the applied voltage, armature voltage, or I suddenly change the load torque, or some other change perhaps. How will the speed change and behave from that moment onwards? So the motor may be already running. So if x is my omega, the speed, angular speed of the motor, then x0 is not going to be 0, but it will be some non-zero value. So rather than say that we will assume that the initial conditions are 0, it is better to say that we are only going to look at the 0 state response part of the total response. In other words, we are only going to look at a part of the response. We will have to look at the other part also to get the actual response or the total response, but for the moment we will only look at the 0 state response. So if we do that, so I can write x, capital X, with the subscript 0 state. So x 0 state as a function of s is simply 1 divided by s plus a0 into u of s. Now this is only for a first order differential equation, but we will see that for second order and higher order differential equations also there will be something which will be like this, and therefore we proceed further and introduce a new concept, namely that of a transfer function. I already mentioned the transfer function as something which may appear in a block diagram, and in a control system, feedback control system block diagram, you will come across transfer functions g of s and h of s. These are the usually chosen symbols for particular transfer functions in the forward path and in the feedback path. So I have already used this word transfer function, but I have not defined it or told you what exactly it is. Now is the time to define it. So look at xzs, the zero state response, but its transform, Laplace transform. On the right hand side we have the input, or rather the Laplace transform of the input, and the fact is that the zero state response transform is 1 divided by s plus a0 multiplied by or multiplying us, or in other words the zero state response transform is the input transform multiplied by some expression. Now that expression in this case is 1 by s plus a0. Does it depend on what ut is? Does it depend on what input we have chosen? No, because what appears here is only the transform of the input, the transform of the zero state response, and this is the relationship between the two. So this 1 by s plus a0 is a multiplying factor which does not depend on what input function we are going to choose. We could choose a constant input 1, we could choose a ramp, we could choose an exponentially decaying input, we could choose a sinusoidal input, anything which is Laplace transformable, for which the Laplace transform makes sense, we can choose that as ut. No matter what ut we choose, the relationship between xzs for that input and that input transform will be by this factor, multiplying back factor 1 by s plus a0. So this 1 by s plus a0 is said to be the transfer function corresponding to the first order differential equation I wrote, and I will rewrite it little differently as d plus a0 x equal to u. The differential operator d plus a0 acting on x gives the input u. This is the differential equation. Correspondingly, the Laplace transform relationship is Laplace transform of not the response but the zero state response part of it equal to this function 1 by s plus a0 multiplying us. I can also rewrite it as x zs zero state response Laplace transform divided by u of s equals 1 by s plus a0, and this is how sometimes a transfer function is defined. A transfer function of a system is defined as the ratio of the Laplace transform of the response to the Laplace transform of the input. In many textbooks you will find the definition in this way: the transfer function of a system is the ratio of the Laplace transform of the response to the Laplace transform of the input that produces that response. Now that definition is not quite correct for several reasons. First of all, it is not the Laplace transform of the response that I am looking at. I am looking at a part of it which does not involve the initial conditions, but which only involves the input. So this is not the whole response. There is the other part which involves the initial conditions, and the initial conditions may not be 0 in a particular situation. So we cannot ignore them. We cannot say put the initial conditions equal to 0, because we may have to study the problem when the initial condition is not 0. So that is one thing. It is only a part of the response whose transform we are taking and dividing it by the Laplace transform of the input, and therefore we get 1 by s plus a0 as the answer. Second thing is, for a general system, not necessarily our induction, our DC motor, or the tacho generator feedback, etc., for which the differential equations were linear, for a general system, of course I can apply some input, I can observe the response. Unfortunately, the observed response, we do not know how much of it is due to the initial conditions being non-zero and how much of it is due to the input. So in general, we cannot from the observed record separate out the zero state response as it is. It's only for linear differential equations with constant coefficients that the response can be separated into two parts, one part involving only the initial conditions, the other part involving only the input. Secondly, for a general system, not necessarily linear, etc., of course I can apply an input, I can observe a response, and I can even compute the Laplace transforms of the two, Laplace transform of the response, Laplace transform of the input. For example, the input may be e raised to minus t, at, no problem, Laplace transform is 1 by s plus a. The response I may recognize as a familiar function, calculate its Laplace transform, and so I can write this ratio, the actual response transform, whatever it is, as a function of s divided by the actual input transform. But the trouble is that will not be something like here 1 by s plus a0. No matter what the input is, the ratio is 1 by s plus a0. Now for a general model, this is not going to happen. The ratio will be different for different inputs, and therefore the concept of transfer function does not make any sense or does not have any use. When I can take something and divide it by something else, what use is it if the result is dependent on what I have chosen as one and what I have chosen as the other thing? So the concept of transfer function is really useful only for systems which are described by ordinary linear differential equations with constant coefficients. No wonder therefore that directly the transfer function idea is not useful for nonlinear systems or for time varying systems. Linear differential equations with constant coefficients, linear. So the transfer function idea is not directly useful for a nonlinear system. Although one tries to extend the idea and therefore one can do something. In fact, there is a method called the describing function approach for studying nonlinear systems, which tries to extend the transfer function idea to nonlinear systems, but it's not exactly the same concept, it's a different concept, describing function. That's why it's called a describing function and not a transfer function. So linear. Second, with constant coefficients, or what are called time invariant systems. If the system is not with constant coefficients, or if the system is time varying, then again the idea of a transfer function will not be useful. Again, in that case one can try to push it through, but then some different concept will have to be applied. In our course we are not going to look at time varying system models or nonlinear system models, so this will not be of any use to us right now. Now as you can notice, the system differential equation I wrote in this operator form, d plus a0 operating on x, the response equal to the input u. The transfer function I have written in the form 1 by s plus a0, or alternately x 0 state s equals 1 by s plus a0 into us. And I suppose you can notice some connection between the operator and the transfer function. In the operator I have d plus a0, in the transfer function I have s plus a0. Of course I have it in the denominator. So maybe from the differential equation itself I could directly write down the transfer function. From d plus a0 I go directly to the transfer function as 1 over s plus a0. Now this is correct. Of course we have to prove that it is correct. So we can take a second order differential equation and see what happens in that case. And I will take a second order differential equation in which on the right hand side I just do not have the input, but I have a derivative of the input also. So first let us take a second order differential equation. So d square plus, remember the notation, a1d plus a0 operating on x equal to u. This is a second order operator, input is u, response is x. If I were to solve this, I will have to know what ut is, calculate its Laplace transform us. What about initial conditions? I will have to know two initial conditions, x0 plus and dx0 plus. The value of x at 0, limit from the right, and the value of the derivative of x at 0, or rather the limit from the right. Knowing these two, knowing ut, if I can compute u of s, I can calculate x of s, and then if I know my Laplace inversion techniques, I can calculate x of t. Let us see what x of s will look like. Here we have d square acting on x, so that if you remember by the derivative formula for a second order derivative will be s squared x of s minus s x0 minus dx0. So this bracketed expression is the Laplace transform of d square x, its value at s. The second term is a1 times the Laplace transform of dx is s xs minus x0. The third term is simply a0x, so its Laplace transform is a0xs equal to us. So if I take the terms involving only x of s, keep them on the left hand side, transfer the other terms involving the initial conditions to the right hand side, what will I get? I will get xs multiplied by s squared, xs multiplied by a1s and x of s multiplied by a0. So I will have s squared plus a1s plus a0 multiplying x of s equal to, what do I get on the right hand side? Let me write down u of s first, plus x0 dx0 terms transferred on the right hand side. So I will write here as some multiplying expression for x0 and some other multiplying expression for dx0. So xs is the response transform, it obeys this equation. Now, like in the first order case, we can see that there are two parts here. One part only involves the input, the other part involves the initial condition or conditions, in this case x0 and dx0. So if I am only going to look at the 0 state response or the response under initial conditions 0, or strictly speaking if I am going to look at the part of the response that only depends on the input, then what will I get? I will have x 0 state of s divided by u of s equals 1 divided by s squared plus a1s plus a0. So I am only looking at a part of the response which depends on the input, and therefore it is what will remain if the initial state was 0. That is why it is normally called the 0 state response, divided by the input transform equal to this ratio 1 divided by s squared plus a1s plus a0. And now one can immediately see that s squared plus a1s plus a0 occurs here in the denominator, whereas the polynomial differential operator is d square plus a1d plus a0. So simply replace d by s, I get the denominator in the transfer function. Hopefully this will happen for higher order differential equations, and you can actually show for yourself that it will happen. So you can try this as an exercise. Write down the third order differential equation, write it as d cube plus a2d square plus a1d plus a0 acting on x equal to u. Take the Laplace transformation or the Laplace transform of both the sides, use the derivative formula appropriately, write down an expression for x of s multiplied by something equal to a sum of a number of terms, pick the term that only involves the input and get the transfer function. You will find that this rule, replace d by s, is indeed correct. In this context, let me mention that transfer function idea, as some students mistakenly remember it, is not the ratio of the output value at any given instant of time to the input value at the same instant of time. So it is not a ratio of the output value at say 0 second or 5 second or 20 seconds to or with the input value at 0 or 5 or 20 seconds. So the transfer function is not x0 divided by u0 or x5 divided by u5 or x20 divided by u20, not even the 0 state response part of the response. No, this is not true. The transfer function is a ratio of transforms, of Laplace transforms. It is not a ratio of output divided by input. Very often students will write in the examination paper or when I conduct interviews and I ask what is the transfer function, this is usually the first response. It is the ratio of output to input. Student does not bother to think what he is saying. It is not. What he means is, or what he should mean is, and therefore he should say that the transfer function is the ratio of the Laplace transform of the response in fact that's not quite true. The Laplace transform of a part of the response that depends only on the input, or that remains when the initial conditions are put equal to 0, to the Laplace transform of the input. And secondly, you should also remember that this concept is useful only for linear time invariant system models, or those which are described by ordinary linear differential equations with constant coefficients. So keep this in mind. Transfer function is not the same thing as gain. Output is 20 volts, input is 1 millivolt, therefore the gain is output voltage divided by input voltage 20,000 or whatever. It is not. The transfer function is not gain in this sense. It is not output voltage divided by input voltage. The transfer function would be Laplace transform of the output voltage divided by the Laplace transform of the input voltage, and the Laplace transform is not the same thing as the value of the function. 5 volts is different from the Laplace transform of a signal which has a value of 5 volts at some particular moment of time. The two are quite different. So don't do that mistake. Transfer function is a ratio of Laplace transforms. It is not a ratio of output to input. Now, when the differential equation was simple like this, the first order differential equation or the second order differential equation where there was only u term on the right hand side, the transfer function I told you could be written down immediately without going through this business of applying the Laplace transformation to the two sides. What if the differential equation is a little more complicated? Let us take for example the second order differential equation, d square plus a1d plus a0 operating on x, but that is no longer equal to the input u. For some reason it is not u, but it is a combination of a derivative of u and u. For example, it may be, now here I am using a notation which is natural, some books use it, others do not. I will write here b1 du dt plus b0 u, that is the right hand side is not just u, but it is a multiple of u added to a multiple of the derivative of u. And of course I do not want to write d on the left hand side and d by dt on the right hand side, so I will rewrite the right hand side as a polynomial differential operator operating on u. That is very easy. I will simply write b1d plus b0 operating on u. Now that is a second order differential equation in x, but it involves first order derivatives of u also, first order derivative of u also. It is a little different from the one where we had just u on the right hand side. However, we can still apply the Laplace transformation to both sides, and what will we get? On the left hand side I have d square plus a1d plus a0 x. So applying the Laplace transformation to that, I will get, as I did earlier, s squared plus a1s plus a0 multiplying x of s, plus I will write terms involving the initial conditions x0 and dx0. That is what I will get on the left hand side when I take the Laplace transform of the left hand side or apply the Laplace transformation to the left hand side, which is a second order differential operator, polynomial differential operator operating on x. What about the Laplace transform of the right hand side? The right hand side is b1d plus b0 operating on u, and using the derivative formula it will turn out to be b1s plus b0 into u of s. But just as there are the initial values of x on the left hand side, because there is a derivative of u on the right hand side, there will be an initial value of u on the right hand side. So plus term involving u0 in this case. So that is the full equation for x of s, and therefore s squared plus a1s plus a0 multiplying x of s equals 3 terms. One is b1s plus b0 into u of s, this involves the input transform, plus terms involving x0 dx0, the initial values of the response, plus a third part is terms, or in this case only one term, involving the initial value of u0. Now as we did earlier, we will only look at this part which involves the transform of the input. It is not that the other parts are 0, they may not be. For example, u0 may not be 0. If it is a constant function 1, then u0 is 1. If it is the function e to the minus t, u0 is 1. If the function is cosine t, u0 is 1. So I can't say u0 equal to 0 because it is not 0. Similarly, x0 may not be 0. I cannot say I will ignore it. As I told you earlier, maybe I am looking at a problem when the motor is already running, and at t equal to 0 I make some changes. So we can't say x0 equal to 0, and I can't solve the problem if x0 is not 0. That is not true. We can solve the problem because we can find out what the terms involving x0, dx0 and u0 are. But if we choose to look at, or if we restrict ourselves to only this term, then the other terms are not being considered right now. Not that they are being neglected, or they can be neglected, or they can be ignored. Many books give you the impression that the other terms do not matter. Now that is not true. We will see later on that these two terms matter. They cannot be ignored. They are not negligible. It is only that we choose to look at one term at the moment. You can't look at the whole world at any one moment of time. So we look at this first, then we look at this, then we see if both are present, what is the effect, and so on. That is what we will do. So if we choose to look at the term that involves only the transform of the input, then this is the term that remains. And now I have xs multiplied by something equal to us multiplied by something, and therefore I can write the ratio for this part of x. There is no name for it. This is a part that involves only the transform of the input, does not involve initial conditions of either the response or the input, divided by u of s equals, in this case now in the numerator I do not have 1, but I have b1s plus b0 divided by s squared plus a1s plus a0. Now look at the differential equation. Could I have obtained this transfer function from the differential equation? In the differential equation I have an operator acting on x on the left hand side, I have an operator acting on u on the right hand side. And look, the operator which was acting on u, the corresponding s thing appears in the numerator of the transfer function, whereas the operator that was acting on d replaced by s appears in the denominator of the transfer function. And so we can go ahead and formulate a rule for writing down the transfer function for a differential equation which need not be of the second order derivative of x, which may have higher order derivatives of u also. And so I will write this equation in the following symbolic form: PD, where PD will stand for a polynomial differential operator. It may be of degree 1, it may be of degree 2, that is differential equation as of first order, second order, it may be of higher degree, it may be of degree 6. PD acting on x, x is the response, equal to QD, Q is another polynomial differential operator acting on the input u. If this is my differential equation model for my system, then if I look at not x of s all of it, but a part of it that only depends on the input transform, then the ratio of that transform of that to the transform of the input will be equal to qs divided by ps, or in other words the transfer function corresponding to this differential equation will be qs divided by ps. We have to remember that the multiplier for u, qd, the corresponding qs is in the numerator, the multiplier or the operator acting on x, the corresponding pd becomes ps in the denominator of the transfer function. Do not interchange the numerator and the denominator. In a hurry sometimes students make this mistake, but there is no reason to make this mistake. You can think of applying the Laplace transformation and almost see that, okay, if I have x squared d square x rather on the left hand side, I will have s squared x of s plus some stuff, so that d is replaced by s, but that multiplies x of s, and therefore it will appear in the denominator when I write the transfer function. Whereas if there is a derivative of u, there will be a corresponding s thing, but that is on the right hand side, therefore when I write it as x divided by u, it will be in the numerator. So the polynomial differential operator which operates on the input is in the numerator, and the polynomial differential operator which operates on the response or output is in the denominator of this transfer function, and the transfer function looks like a ratio qs by ps, and qs and ps are actually two polynomials. So such a function is called a rational function. In the theory of functions of a complex variable, such functions are known as rational functions. They are ratios of two polynomials. As an example, such a rational function may be the numerator is s plus 1 and the denominator is s squared plus 5s plus 6. And if I ask you, well, what kind of differential equation or what differential equation could it be for which you obtain this transfer function? The inverse question. Given the differential equation, find out the transfer function. With little practice, you will be able to do it without any delay. Simply replace d by s kind of thing appropriately, you will get the transfer function. Now the inverse question, given the transfer function, to what differential equation it may correspond, that is, for what differential equation could it be the transfer function? And the answer is not difficult. Do the opposite, replace s by d, only use the operators properly. Something operates on u, something else operates on x. So in this case, what will be the differential equation? S plus 1 is in the numerator, so d plus 1 operating on u, s squared plus 5s plus 6 is in the denominator, so s squared plus 5s plus 6 operating on x, and therefore the differential equation will be d square plus 5d plus 6 operating on x equals d plus 1 operating on u. If you started with this differential equation, by applying the Laplace transformation and by choosing to look at only a part of the response, you will obtain precisely this transfer function. So it's not difficult to go back from the transfer function to the differential equation. It's as simple as that. Remember that we are not looking at the response, we are only looking at a part of the response, a part of the response that depends only on the input transform. It does not involve the terms, or it does not look at the terms that involve the initial conditions or initial values of the response, nor the initial conditions or initial values of the input. It is only looking at one term which involves the input transform, and it so happens that that part divided by us is something which does not depend on the input transform, nor on the input initial conditions, nor on the response initial conditions. It only depends on the operators that are involved in the description of the system. If this is the differential equation for the system, then for this system, this is the transfer function. Now of course there is a way of sort of getting this which is not really completely justified, and that is to rewrite this equation as x divided by u equal to d plus 1 divided by d square plus 5d plus 6. I will put it in inverted commas. Why? Because first of all, as I told you, the transfer function is not xt divided by ut at t equal to 0 or 5 or 20 or 10 raised to 3 seconds or whatever. It is not a ratio of output or response value to input value. No, it is a ratio of Laplace transform. So on the left hand side, x by u makes no sense. I can of course take xt divided by ut, but that is not the transfer function. But I am committing another crime. On the right hand side I am writing d plus 1 divided by d square plus 5d plus 6. Now I know what d plus 1 is. It is an operator acting on u does something, or the other operator acting on x does something to it. But what is this d plus 1 divided by d square plus 5d plus 6? What is it that I am supposed to be doing? At this stage it is not immediately clear that this can be interpreted as an operator, but in advanced mathematics courses one can give some meaning to this, so that this becomes an operator, which is an operator which is not a polynomial differential operator, but it is a rational differential operator. But at this stage of our course we are not going to look at that at all, so we will say that this just does not make sense. But to remember how to get the transfer function, this is okay. It is as if I write x by u equal to d plus 1 by this and then replace coolly d by s. It is not the justification, but it is a shortcut to just remembering what the transfer function can be or how I can obtain it from the differential equation. So long as you know what you are doing, it is okay. Do not make the mistake of thinking that this is the way in which you show that the transfer function is s plus 1 divided by s square plus 5s plus 6. No, this is only a way of remembering or a shortcut to writing down the transfer function, so that you don't make the mistake of putting the wrong operator in the numerator or the corresponding s polynomial in the numerator and something else in the denominator. The numerator and denominator polynomials should not get interchanged in their positions. So just to remind ourselves, or to keep, enable us to do it quickly, this is okay, but this is not correct, this is nonsense. On the one hand, I have operators and I don't know what their ratio means. On the other hand, I have input and response values, but that is a number, and this is operator, if at all it can be interpreted, just doesn't make sense. Alright, so we have the concept of a transfer function for a system differential equation which is PDX equal to QDU, a linear ordinary differential equation with constant coefficients in which not only derivatives of the response may appear, but the derivatives of the input may also appear. And we will see soon, when we use feedback of various kinds, that you can indeed have an equation in which the derivative of the input appears in the differential equation. So it is necessary to look at a differential equation in which what you have on the right hand side is not just u, but QD operating on u. So it is not just for the sake of generality that I am doing it. We will come across situations where this will happen. There will be derivatives of the input occurring on the right hand side of the equation. There will be systems, in fact our very motor control problem, where this will appear. As I told you earlier, the main purpose of having this concept of a transfer function, and in fact using the Laplace transformation, defining the Laplace transform and so on, is not really to compute responses or solve differential equations. In fact, from the beginning I have been telling you that today, 2004, we have progressed quite a bit beyond what the situation was 10 or 20 or 50 years ago. The Laplace transformation method was evolved sometime in the first and second decade of the 20th century, 1910, 1920, a formal definition of the Laplace transform or the Laplace transformation, and then its use for solving differential equations or studying differential equations and so on. The primary aim is to get some idea, to get some insight into the behavior of systems, into what will happen if I change this or if I change that. It is of course necessary to do some computations, but today we have computer programs or software which will do the computations for us. If I have a differential equation like PDX equal to QDU for say P of third order, or a polynomial of degree 3, maybe Q, a polynomial of degree 2, and I know the input function ut is say sin t or e to the minus t. There are programs in which all I have to do is simply to input this data, that is this differential equation, because I can't simply put this into the computer, there is no way. I can only push in a floppy or a CD into a computer. I cannot write a differential equation on a piece of paper and then put it in somewhere. We don't have smart enough computers, someday we may. So all I do is scribble on a piece of paper the differential equation, write down ut equal to sin t, write down x0 equal to this, dx0 equal to this, and just push it into some box or some slot of on the computer or on the terminal or whatever I see in front of me, and the computer program or the computer takes over and finally shows me on the screen the response or gives me a printout. No, today we are not able to do that. But if I can input the data about the equation in a proper format, input the function also, that is say something about the input function, and input the initial conditions, then these programs will compute the response, and they will not be taking Laplace transform by applying some laws of the or the rules of the Laplace transformation at all, and they will also in fact not compute the exact solution, but they end up computing only good approximations to the solution. So they will not only compute and then give you a printout, they can also plot. So for solving differential equations, to get the solution numerically, numerical values or plots, I don't have to really use the Laplace transformation method and do it all by myself. There are programs available to do it. Of course, if I don't have the programs, then I may have to do it myself, like I showed you for a second order differential equation how I might obtain the transfer function. And then of course, if I know ut, I can find out us, etc. I can actually calculate excess, get inverse, and so on. So if no program or packages are available, no software is available, then of course you and I may have to do it all by ourselves. But the purpose is not therefore only computing, or if we may not even compute. The purpose, to repeat Hamming's admonition, is purpose of computing is insight, not number. So what kind of insight can we get from this? And we will see that we will indeed get some insight. If I have a transfer function which is s plus 1 divided by s squared plus 5s plus 6, then if I want to find out, or if I want to compute the response, then of course I have to know ut, I have to calculate us, then I have to multiply us by this, and then find out the Laplace inverse of this, which will involve a lot of work. Of course I have to first find out what us is, it will depend on what ut is. I may have to look up a table of transforms if I have forgotten or if I don't remember. Then I will get a messy expression involving s, I have to find out its Laplace inverse. I may use a technique which I mentioned earlier, the partial fraction expansion technique, or use some other technique, use the complex inversion integral to find the original function knowing the Laplace transform, and so on. But is there something that I can do without, or which will not involve actual computation? And the answer is yes, and that is what I would like to tell you about. So I have the transfer function which looks like this. What can I say about the response, or can I say something about the response by looking at the transfer function without even knowing what the input may be? Of course, let me repeat once again, what we are looking at is only a part of the response. It is not the response, or it is not the whole response. I am not looking at some other terms which are important, which cannot be neglected all the time. Therefore, we have to consider them also. Right now we are only considering a part of the response. Keep this in mind all the time. But what can I say about this part of the response? In fact, we will see that we can say something not about this part of the response, but actually even a further part of it. But we can say something. But in order to say something, it is necessary to go one step further, and that is why I have chosen a particular transfer function in which the numerator is s plus 1, but the denominator is a quadratic, it is s squared plus 5s plus 6. Now in order to get some insight out of this, I should not leave it just as s squared plus 5s plus 6. What should I do with it? I told you that one of the problems which one encounters in control systems is factorization of a polynomial, or finding the roots of a polynomial. This you will find is a problem which, no matter what technique you use, unless you are just giving something to a computer program, therefore you don't have to do anything except inputting the data properly, factorizing a polynomial or finding out the roots of a polynomial is something which is required. You may not do it, the computer program will do it. In this case, or for the example that I have before you, I have chosen the denominator polynomial s squared plus 5s plus 6 so that it can be factorized quite nicely. In fact, you should be able to immediately find out its factors. The two factors are s plus 2 and s plus 3. I have chosen the example as a very simple one, so the factorization is also very simple or easy. You can use the roots of a quadratic formula, or you can just do it somehow. You have done it in school algebra. S squared plus 5s plus 6 factorizes as s plus 2 into s plus 3. Just verify that it does correctly. So now I have a transfer function in which the numerator is already in factorized form because there is only one factor. The denominator was not in the factorized form, but I have now its two factors, s plus 2 and s plus 3. Now this is something which one can think of doing for any transfer function which looks like a ratio of two polynomials, as we have seen here, qs divided by ps. We can imagine that qs is factorized, we can imagine that ps is factorized. If we do that, then in the numerator we will have a number of factors, linear factors. In the denominator we will have a number of linear factors. The information about the transfer function is therefore presented in a different manner in the form of factorized polynomials. From this, then one can go one step further and represent this information in a graphical or in a pictorial way, and we will find that this way of representing the transfer function is going to be useful to us. We will look at a method known as the root locus method, which is based on this idea of starting with a graphical or pictorial representation of a transfer function. It is not very difficult to write down this representation, but again you must be careful. So first of all, I am going to represent the information which is present here. What do I see here? I see factors, linear factors, s plus 1 in the numerator, s plus 2, s plus 3 in the denominator. We will transfer this or represent this information in a different way by going back to the concept of the complex plane, in which we represent complex numbers. Of course, complex includes real numbers, so real numbers as well. How do we do it? Well, there is s plus 1 in the numerator. That s plus 1 factor corresponds to a root of minus 1, value minus 1. S plus 1 is 0 when s is minus 1. So this is a bit of information about the numerator factor. There is only one factor, there is only minus 1. Now this root is called a 0 of the transfer function. This is a terminology which control people have developed and have used. The word 0 has a slightly different meaning in mathematics. The word 0 has this specific meaning in control theory. Or when you talk about the 0 of a transfer function, this is what we mean. The transfer function is a ratio of two polynomials. I am looking at the numerator polynomial, I factorize it and I find out its roots, show them on the complex plane or on the Argand diagram. And how do I show it? Now again one makes a convention. It is the numerator, so its roots are shown by means of small circles. So I will put a circle here and I will write down here minus 1 or minus 1 plus j 0. So this is referred to as a 0 of the transfer function, and it is shown by a small circle, not by a dot but by a small circle. This is only a way of representing it. This circle does not mean it is 0 or whatever. I have to write here, of course, the actual root value minus 1 plus j 0 as I have done here. There is nothing else in the numerator, so there is only one circle or there is only one 0. Now let us turn to the denominator. The denominator has not one but two factors, s plus 2, s plus 3. For s plus 2 the root is minus 2, or for s plus 3 the root is minus 3. So there are two factors, there are two roots. I will show them now on the diagram by using a different symbol, not this circle, but by using crosses. So I will put a cross here, and I am not showing this on scale because otherwise my diagram will get cluttered. So I put one cross here and I will put down the location or the value minus 2 plus j 0, and I will put down one more cross corresponding to minus 3 plus j 0. Now these crosses or these roots which correspond to the denominator are called poles. They are called poles of the system or poles of the differential equation or poles of the transfer function. So what do I have so far? I have a transfer function for which there is only one 0 corresponding to minus 1, which means there is only one factor s plus 1, and that is in the numerator, mind you. for the denominator I have two factors, s plus 2 corresponding to this pole at minus 2 and s plus 3 corresponding to the pole at minus 3. So, the denominator is s plus 2 into s plus 3. So, instead of writing down a transfer function as s plus 1 into s plus 2 divided by s plus 3 as a rational fraction, or even s plus 1 divided by s squared plus 5s plus 6, I will represent this transfer function by means of this diagram, and for an obvious reason is going to be called what? What do you have on the diagram? I have poles, I have zeros, of course I can say zeros and poles. The standard terminology for this is pole zero diagram. So, such a diagram is known as the pole zero diagram of a transfer function or of a differential equation or of a system. It shows the zeros which correspond to the numerator factors, they correspond to the differential operator operating on u. The poles correspond to the factors in the denominator, they correspond to the polynomial differential operator operating on the response. This is the pole zero diagram. Of course, one may have to have something more, because for a particular differential equation when I factorize it, the factorization may be as follows. Instead of s plus 1 in the numerator, I may have s plus 1 multiplied by some coefficient or some number, for example 2, and in the denominator of course I may also have a number, let us say 5. So, I could have a multiplier in the numerator, I could have a multiplier in the denominator, but instead of keeping them separately, because I could write this as 0.4 into s plus 1 divided by s plus 2 into s plus 3. So, if I agree that the polynomial will be written in this form, that the numerator factors and denominator factors will be of the type s plus something, where that something could be positive, negative number, real or complex or imaginary, whatever it is, and this whole thing will be multiplied by a number, then all I have to specify is, in addition to the zeros and the poles or the locations of the 0, in this case minus 1, locations of the poles minus 2 and minus 3, I have to specify also this multiplying coefficient 0.4, and I can put it down as a number on the pole zero diagram somewhere. Let us say I put here 0.4 in brackets or encircle it like this. This could be called the gain of the system, but the word gain is used in so many different ways that it is better not to call it gain. Let us reserve the term gain for what is normally called gain, in fact decibel gain, gain in decibels. But remember that this coefficient may not be 1, and so it may be necessary to be told what exactly this coefficient is. Remember that we had a differential operator b1d plus b0, and so we got b1s plus b0 in the numerator, and so in order to write it as in the factored form, I will have to pull out that coefficient b1 and write this as b1 into s plus b0 divided by b1. So, I may get a non-unity coefficient multiplying, therefore I have to write it. If it was 1, I can suppress it. If it is not 1, I have to write it like 0.4. And so, this can appear on the pole zero diagram, or I can put a statement saying that this coefficient will be 0.4 or whatever it is. So, the transfer function information can be shown as a pole zero diagram, and we will see that this diagrammatic representation is going to be useful as we proceed further.